What up, y'all? It's Chem Thug. Happy New Year. Today, I want to do something a little different. I thought about it, and I make a lot of comments about atoms and molecules in my videos, and maybe it'd be nice for people to have a little reference that discusses what atoms are and why they come together to make molecules. So that's what this video is going to be. So one of the oldest questions of humanity has always been, how many times can I break something before it's not that something anymore? The idea of fundamental elements to our reality is something that's been with us for a long time, and this guy Democritus is oftentimes credited with being the first person to think of atoms. Although, in order to really understand atoms, you need a lot of equipment that they could not have had then, so we kind of just scrapped the atoms part and kept the fundamental elements part for another couple thousand years. And then after discovering a bunch of these actual fundamental elements and recognizing that it's not fire, air, earth, and water, nor is it psychic, flying, poison, or fighting, it's actually all these little squares on the periodic table. And each one of those squares has its own specific kind of atom. And atoms represent the most fundamental components of the chemical elements around us. Now, at some point, somebody has probably said to you that you can think of atoms as building blocks. And from the perspective of chemistry, this is pretty true. You won't find lone atoms just kind of floating around in space like that. Generally speaking, all of the atoms of the various elements on the periodic table will come together to make what's called molecules, except for one group of those atoms, the noble gases, the ones all the way at the end of the periodic table, helium, neon, argon. They don't form molecules. You will find their atoms just kind of floating around in space as lone atoms. And we believe that most atoms want to be like the atoms of the noble gases. And this is where molecules ultimately come from. But in order to really explain that and for that to make sense, I got to start talking about the parts of an atom. So let's get into that. So atoms have three parts to them: protons, neutrons, and electrons. So first we're going to talk about the protons. Protons live in the nucleus, the center of the atom, and they have a positive charge. Protons, they're just positively charged. It's just a thing about them. It's fundamental to being a proton, but they also have two very important jobs in the atom. One of the important jobs they have is identifying what element that atom belongs to. So if you look at the periodic table, you'll see that each one of those squares has a whole number on it. And that whole number is what's called the atomic number. And that number tells you how many protons are in the nucleus of the atoms that belong to that element. So if you were just like kicking around in space as a cosmic being and you could just like pluck an atom from the ether and count the number of protons in its nucleus, you could say, yeah, that's an atom of carbon if there's 6 protons, or it's oxygen if there's 8 protons, you know. The other job that protons have, though, is to pull electrons to the atom. And we're going to talk about the electrons in a second. But you might be wondering at this point, if there's more than one proton in the nucleus of the atom, how do they all stay there without the positive charge making them just like yeet each other out of the nucleus? The neutron. So the neutron is the second part of the atom. It also lives in the nucleus with the proton, and it does not have a charge. Its job primarily is to hold the nucleus together. The presence of the neutrons helps to mitigate the repulsive force between those positively charged protons in the nucleus. And so the more protons that a nucleus has, it's more likely it's going to have more neutrons. Unlike the proton, neutrons don't really identify the element. You can have two atoms with the same number of protons that have different numbers of neutrons. And this just results in what's kind of just like a different flavor of that element. An example of this that a lot of people might be familiar with is, well, hydrogen. H1 hydrogen, the most common version of hydrogen that we find, only has a proton in its nucleus. And if you want a fancy name for it, you can call it protium. But another isotope of hydrogen, deuterium, has a proton and a neutron in its nucleus. They're both hydrogen, and for the most part, the chemistry is generally going to be all the same, with the exception of things like the kinetic isotope effect, which is outside the scope of this video. And this is ultimately why we identify elements by the proton, because it's kind of the one part of the atom that really can't change. And if it does change, then the chemistry changes. What it can bond to changes. All kinds of things start to change. The neutrons are really just there to kind of glue the protons together. And unless we're talking about actual nuclear chemistry, they don't really do a lot. But now we get to talk about that third part of the atom, the part that I'm always the most excited about, the electrons. So electrons are arguably the most important particle to organic chemistry, period. But it's arguable, I guess. Electrons have a negative charge, and their negative charge is the same strength as the proton's positive charge. So for every proton that an atom has, according to its atomic number, it will also have that many electrons that just kind of come with the atom. Now, as I mentioned, the electrons are drawn to the protons in the nucleus, but the electrons, they don't live in the nucleus because electrons are really small. They're much smaller than protons, which are already smaller than atoms, and you can't see atoms, right? So electrons have to live by those funky quantum rules that we have a lot of experimental evidence that kind of shows that these rules hold in almost all cases. And we also have a lot of math that kind of explains why these rules make sense. But I'm not really going to talk about the math. I'm really just going to give you the rules that these experiments and this math has elucidated for us. So the first rule is that they can't stop moving. Because they're so small, they're quantum bodies, they can't sit still, they got to keep moving, constantly moving, and they don't live in the nucleus for this reason. They live in their own section of the atom called the electron cloud. Now, the electrons are negatively charged though, and they don't have neutrons like the protons do in the nucleus that kind of helps to space out that charge. So the electrons have to arrange themselves in this electron cloud so that they don't get too close to each other, but they can all still feel the protons in the nucleus because that's what they're there for in the first place. And these arrangements that they make for themselves in this cloud are called orbitals, and they come in sets called shells. The next rule is that when these electrons are in these orbitals in the electron cloud, they got to have a roommate electron. And this one might sound really weird because we've just been talking about the whole they want to be they're negative and they got to space out. But this is one of those ones that we kind of understand from experiments. You've heard of free radicals, I'm sure. Free radicals are electrons that are in these orbitals without roommates, and they tear things up. Radical oxidative stress is a thing. This is how we know that this rule exists. Electrons kind of got to have a roommate in these orbitals. Now, the third rule is a little tricky to get, but when you have orbitals that are the same, the electrons got to spread out into the orbitals. You can't just 1, 2, 1, 2, 1, 2. You got to go 1, 1, 1, 2, 2, 2. Kind of like how you deal cards. Why? In large part, the negative charge. Can't just pile up on each other when there's space available to spread out. Now, there is a fourth rule, but with these first three rules, we can start to build a neon atom, and that'll make a lot of this stuff make a lot more sense, and it's going to be fun, so come on, let's do it. So neon is atomic number 10. One of the noble gases, has 10 protons, 10 electrons that need to live in this electron cloud around that nucleus. So you can imagine the nucleus is just kind of like this hard little ball in the middle of just kind of floating in space. And you got 10 electrons lined up one at a time, trying to make orbitals around this nucleus. First electron, it's like, oh, I'm just going to set up a little ball right around the nucleus, kind of like the candy coating on a lollipop or a jawbreaker, right? And so it moves into this one orbital and it just starts doing this dance thing. And then electron number 2 says, oh, you need a roommate, don't you? Pops itself in there with that other with the other electron in this first orbital, and that's your first shell. That's the first orbital shell, first one around the nucleus. Can't fit more than 2 electrons in this one. So you got 8 more electrons, and the third one is like, all right, well, I can't fit in this first shell. I guess I'll just make the second shell. So now there's a second shell. It's just larger than the first shell. And this is the larger area around this nucleus where the electrons can reside. Electron 3 decides to make an orbital that looks just like that first one. It's just another ball, a bigger ball around that first ball. And then electron number 4 comes along and says, hey, you need a roommate, don't you? And electron 3 is like, yep, I do. So electron 4 moves in. And now you've got your first shell, second shell, right? Now I said the second shell is bigger, right? It's further away from the nucleus. And so it can fit 3 more orbitals. But these 3 orbitals don't look the same as those first 2. These 3 orbitals are kind of shaped like an hourglass because math says they are. And where the very narrow middle of this hourglass goes through the nucleus of the atom, and then you've got 2 lobes kind of sticking out from the sides of the atom. Now there are 3 of these, and they're kind of turned as far away from each other as they can be, so that it ends up, the shape it takes ends up looking like a jacks for knuckle bones, with these three separate orbitals, electrons 5, 6, and 7 each take one orbital. Because remember, we got to deal them like cards. They can't just all go in pairs. So 5, 6, and 7 go into one, and then 8, 9, and 10 become roommates with those three, and we're done. That's a neon atom. It's happy. It's floating in space. It's not making molecules. It doesn't do anything because it's a noble gas, and all of its electron shells are filled. So what I just described to you is something generally referred to as the octet rule, which has a lot of weird exceptions that I'm going to avoid here. But the general idea is that electrons in atoms kind of need to come in these filled shell sets. And the noble gases all by themselves have enough electrons to fulfill these shells, which incidentally, it's usually 8 electrons. That's why it's the octet rule. The problem happens though, if you're the atom of an element that does not just come with enough electrons to satisfy the octet rule. Then you kind of got a problem. And we can look at this problem with oxygen so we get a better idea of what happens when an atom runs into this situation. So oxygen is atomic number 8, meaning it has 8 protons and it comes with 8 electrons. And maybe you're already seeing the problem here. But the setup is all the same. It's always the same with an atom. You get your first shell, 2 electrons, they go in, move in, happy. Then you get your second shell, electron 3 moves in, and then electron 4 moves in as his roommate. But now we're on the second shell, we've got our hourglass rooms, and we've got electrons 5, 6, 7, and 8. And we've got 3 rooms that each hold 2 electrons. So 5, 6, and 7, well, they each take one separate room as they have to, and then 8 just moves in as a roommate with 5, and 6 and 7 kind of just like panic. They're like, yo, wait, whoa, what? I need a roommate. And this is the problem that the atoms of most elements find themselves in. Now, there are 2 ways that atoms from other elements can fix this problem. One way is by sharing electrons, what's called covalent bonding. How do you share electrons between 2 atoms? Let's take another oxygen atom. Just like the first oxygen atom, it's got its orbitals all set up with its electrons, but it's got 2 electrons in 2 of those orbitals that don't have roommates. And how nice would it be if those 2 oxygen atoms got close enough to each other that the orbitals that only have 1 electron each could kind of just overlap with each other, just kind of the way like bubbles do in water, and join. And at that point, you've got 2 electrons in 1 orbital. They got their roommate satisfied. But also, since it's just 1 orbital now between the 2 atoms, each atom gets to feel a little bit more like it's a noble gas. Because now oxygen atom A technically has 2 electrons, but so does oxygen atom B. It's also kind of got 2 electrons. And the electrons, because they're there for the protons in the first place, well, these electrons get to be a little special because the 2 electrons that are between the 2 atoms, well, they get to feel the protons from both atoms too, which is what the electrons want to begin with. So when you get electrons that can do this kind of thing, they're generally pretty happy to do it. They're usually pretty glad as long as you can get those 2 orbitals to fit over each other in space well. And when you can get more than one of those orbitals to do that, say like, we're talking about the first 2 of those hourglass rooms, you kind of got the other 2 that are sticking out up and above it, those kind of overlap too. And that's where you get a double bond. And now we're talking about an oxygen molecule, which incidentally, that's actually what you breathe. You don't breathe oxygen atoms, you breathe oxygen molecules, because oxygen happens to be a fairly reactive molecule, and in part because the overlap on that second set of orbitals isn't that great, just to give you a little teaser for how deep this goes. But at the end of the day, the 2 oxygen atoms fix this problem that they have by just getting close enough to each other that those orbitals and their electron clouds can kind of overlap with each other. They just become a space that the electrons can occupy. At which point the electrons are happy, they got their roommates, the octet rule is satisfied, and you've got a relatively stable molecule. I told you though, there's another way that atoms from elements that aren't the noble gases can fix this octet rule situation and get their shells filled. It's not just through sharing electrons. They can also just kind of exchange electrons. And instead of being atoms, they become ions. So let's take calcium as an example, because I think calcium is an element everybody's fairly familiar with. It's essential to the body and all of that. But calcium's a big boy. Calcium has 20 protons in its nucleus, which means it has 20 electrons to deal with. But I trust you at this point. I think we can make the calcium atom happen in order to illustrate this example. So we're going to run through it real quick because like I said, it's always the same. 28 protons, 20 electrons. First 2 electrons, they go into that first shell. Then shell number 2 holds a total of 8 electrons. 8 of the remaining electrons go into the second shell. So 10 electrons are dealt with. We got 10 more electrons that got to be housed. The third shell is just like the second shell for the most part. And it fits 8 electrons before you got to start dealing with other weird rules. So of the last 10 electrons, 8 move into that third shell, and they're going to be fine. So now you've got 2 electrons left. These last 2 electrons, they're in like that nosebleed shell. You feel me? Like they're far from the nucleus. They don't feel those protons. They can't even see those protons. So they're like, yo, is there another atom we could just like go live on and you just kind of don't have to worry about this fourth shell? You can just have a third shell, kind of like argon, which is also a noble gas. And the calcium is like, you know what, I got you, hold up. So calcium hits up his boy oxygen. And he's like, yo, oxygen, look, I know you got those 2 spots where you need 2 electrons. And I got these 2 electrons that need a crib. Can you adopt these electrons? Can you take them and then I'll be free and not have to worry about this fourth shell? My octet will be satisfied. And oxygen is like, you know, that would satisfy my octet too, dog. But then I gotta be an ion. The calcium's like, I gotta be an ion too. That's cool, dog. So the calcium decides that it's just gonna shove these 2 electrons into the oxygen's orbitals. So now the oxygen has 2 additional electrons over the number of protons it comes with. This makes it not a neutral atom anymore. Now it's an ion, a negatively charged ion, because it has 2 additional negative charges. But the same thing kind of happens to the calcium, right? Because those 2 electrons came from the calcium. And so now the calcium is short 2 electrons, has 2 extra protons. This makes it a positively charged ion, what's called a cation. And now, I think we all remember what happens when you get positive and negative charges next to each other. They stick to each other. And so the calcium cation and the oxygen anion just kind of hang out next to each other the same way that the negative and the positive end of a magnet just kind of stick to each other. And they're kind of stuck to each other for a very long time. The molecule that we just made is a salt. It's called calcium oxide. It's one of the key components of concrete, a very strong, very stable material. Because ionic bonding, this process where one atom just gives away a few electrons to another atom that can hold on to those electrons and it satisfies their octets, is the other way that atoms come together, making molecules and become like the noble gases. That is to say, satisfy that octet rule. Now that I think about it, I did do a video on salts. Maybe go check that one out also if you want another explanation of ionic bonding. But in short, all salts are ionic compounds. They are ionically bound to each other. You can have molecules, whole molecules, that are also ions. But that's not what we're talking about right now. Right now, we're just talking about individual atoms that become ions. But you can have whole molecules that can do that. Go check out the salt video. Go watch it. But to kind of summarize, this process of sharing electrons between 2 atoms, called covalent bonding, and this other process of exchanging electrons between 2 atoms, called ionic bonding, are the ways in which the atoms of non-noble gas elements become like the atoms of noble gas elements. That is to say, they satisfy that octet rule, where their shells get to be filled. As far as we can tell, this provides such an overwhelming amount of stability to the particles involved in the process of bonding that it is simply a thing that happens. And as I said, we really only understand this after thousands of years of people looking at these various reactions and processes in whatever ways they could and coming to these conclusions that hold every time we check them. But yeah, I hope now you have a bit more of an understanding of like what an atom is and why atoms become molecules. And maybe you can look at the world around you a little bit more differently in a little bit more deeper and nuanced way. And to kind of start that, I got a question for you. As I mentioned earlier, hydrogen 1, only has a proton in its nucleus. So if hydrogen 1 becomes a cation, what is it? Leave the answer in the comments, along with any follow-up questions you have. And I just want to say thank you so very, very much for watching to the end. I hope you enjoyed this one. I hope you learned something that you maybe were hoping to learn or didn't expect to learn. Before I go, I want to say a quick and special thank you to the people who support me on Patreon and on Ko-fi. I really, really appreciate that support. It makes it so much easier for me to try and do this full time. And if you're interested in joining those lovely people, I invite you to check out the links in my bio. And until next time, it's Chem Thug.